Hi. Sorry, I was wondering what happened to book. Actually, we were doing some work and couldn't keep track of the time. Come, pull another chair if possible. You want to come or? Okay. He's bringing a chair, huh? Yeah. Okay, good evening, everyone. So it's almost 2/3. Yeah. Yeah. Yeah, one question is already there, right? How do you, yeah. Yeah, that's the most general question. How have you motivated yourself to study physics harder? Uh, see, nobody should do this harder thing, okay? You should take up your passion. If you like certain things, then nothing looks hard. You get into it and you completely immerse in it. You enjoy and you do things. Okay. So there is no question of pushing yourself harder. You work hard and go more and more into depth, but because you like it. Okay? That is what I would say. And interestingly, group theory is a very nice tool to understand many things in a very elegant fashion. Not everything you can get, but there are certain things which you can get using the tools of group theory. Okay, so that's the thing which I would like to convey in the course. And you're already 2/3, 8 weeks or 9 weeks are over. So you have another 3 weeks. So you should be able to appreciate that fact. I hope you're appreciating. There's a question by Ayan Kayal. Madam, I didn't understand the concept of weight. Weights have been done already? Yeah. Yeah. The character table and these things have been done. Character table is done. Yeah. Weight in the context of Lie algebra.
In 9 and 10 assignment case.
The weights of SU2 or SU3?
I didn't go through like the whole lecture, but there was few.
Can you just clarify for me where exactly I am? You are looking into weight in the context of Lie algebra. So simple cases like angular momentum, the weights are just the magnetic quantum numbers. Okay. But if you go to SU3, then you start looking at the weight space. So have you already seen the SU3? Please let me know, then I can answer your question. Basically, these are various states allowed. Okay. So if I give you a spin 1 state, then the spin 1 state allows 3 possible quantum states with magnetic quantum number being -1, +1, and 0. Those are called the 3 weight states associated with the spin 1 object. So that is the way you have to view. And Lie algebra, of course, will involve a set of generators with Lie bracket or commutator bracket. Should be closed, should be a linear combination of these generators. Okay. And then we start looking at the spaces where so you start looking at the eigenstates. So especially if you start seeing that there are 2 diagonal generators, then you write the eigenstates as eigenstates of the 2 diagonal generators. If it is SU3, there are 2 diagonal generators. And the eigenvalues of those 2 diagonal generators will give you the, the points on the weight lattice. Is that done in the week 9 and 10? That I have explained the SU3 octet, decimate and all already.
Yeah, there was few questions from SU2, SU3, some
Okay.
question from the
Yeah, please elaborate if you need anything more, Ian. Then I can explain it. I can work it out and explain. Okay, so if you take SU2, you have J plus, J minus, and JZ, all the generators. You can write the algebra, which is what you call the Lie algebra. This will be twice JZ, and JZ with J plus or minus will be plus or minus J plus or minus. Okay. So you can write a state Jm, which is a simultaneous eigenstate of J squared with J into J plus 1 H cross squared Jm. You can write the Jz on Jm, the Z component of the operator Jz. That will give you Mh cross Jm. Okay, so Jm is a simultaneous eigenstate of J squared and Jz. If you want to generate all the states, M takes values from minus J plus 1, minus J plus 2, and so on, and it goes on till J. So this number of values is 2J plus 1. That's why when I write Jm, we say that there are 2m plus 1, or sorry, 2J plus 1 states. These are sometimes called as the weight states. And you can take a line, say that this is, let's say J equal to 2, then you will have M equal to 2, M equal to 1, M equal to 0, M equal to minus 1, and M equal to minus 2. Okay. So these 5 states are called the weight states associated with the J equal to 2, M equal to 2 is the highest weight states. And to go from one to the other, you can apply J minus operator, which is the lowering operator, can take you to M equal to 2. You can again apply J minus. You can start doing J minus. It's 2 J minus. If I do one more J minus, what happens? It's 0. It doesn't go anywhere. So this is the lower state. M equal to minus 2 is the lower state. And beyond that, you cannot go by J minus operation for a J equal to 2 state. Okay. So those are the weight states for the SU2 Lie algebra. You can continue for SU3. So what is SU3? SU3 is a set of unitary operators. SU3 group is a set of unitary operators. Okay. And the number of independent parameters which satisfies U dagger U to be identity and determinant plus 1 turns out to be 8 generators. Okay. And out of these 8 generators, just like you had in SU2 a JZ, which was a diagonal matrix, here you can have an operator which we call it as lambda 3 and lambda 8, which are diagonal matrices. So you can start writing the state as an eigenstate of lambda 3 and lambda 8, some numbers, and you can put it on the lambda 3 eigenvalue and lambda 8 eigenvalue, you start seeing. Like, for example, if you are looking at the octet, you may end up getting something like this. These are the diagrams you can get for a weight space which is corresponding to the octet state. Okay, so you can see that this corresponds to octet, and similarly you can find this for a decimet also, and you can plot them. See that there are 1, 2, 3, 4, 1, 2, 3, then you have 1 and 2, and then a 1. So there are 10 states in that wait state for a disk. Okay. So these are various ways in which you can. This is what we call it as a wait diagram. So if you go to SU4, it becomes a 3-dimensional, not a 2-dimensional. SU2 is just a 1-dimensional line. But if you go to SU3, various these are octet is one representation, decimal is one representation. And you can start finding what are the ladder operators which can take you from one to the other. And there are not just one ladder operator like SU2, you will have 3 sets of SU2 ladder operators to play around.
So he's asking, is each point in this space
a
weight? So that is a question.
Is the point, is the weight. Yeah, it is called the weight vector, which is the eigenstate of both the diagonal generators. So if you know what is the eigenvalue of this and eigenvalue of this, you can go and plot on this lambda 3, lambda 8, the diagram, that corresponding point. Okay. Suppose this point is let's say 1 and half or something, right? You can plot that by going and putting that point. That's a weight.
So weight state are eigenvalues of
Eigenstates of the two diagonal generators. And you can achieve the weight other states within this multiplet by doing the raising and lowering operators of the Lie algebra. So Lie algebra of SU3 has not just J plus J minus. There are, you can write lambda 1 plus or minus I lambda 2 is your conventional J plus minus, but you can also have lambda 4 plus or minus lambda 5. You can call it as U plus or minus, and you can also have lambda 6 plus or minus lambda 7 as V plus or minus. You can apply these things and you can go from one state to the other state, the way we did in the earlier slide for the J plus and J minus. So this side will be J plus, but if I'm going to go this way, then you have a U minus. Yeah. So this is called weight diagram, and every point in that representation weight diagram corresponds to the eigenvalues of the two diagonal generators. That's the way you have to interpret. Am I answering your question, Ayan Pearl? Anybody else? How many of them have joined? So Gelman matrices are the diagonal, lambda 3 and lambda 8 are the diagonal part of the Gelman matrices. The others are also the matrices which are forms the SU3 generators are given by the Gelman matrices. Works? Yeah.
Yeah, there is one more question. What is meant by left invariant operation?
Okay, so basically you can apply the operation from the left or the right because these are matrix representations. It is it depends on whether you operate from the left or from the right. So many of these conventions, just like we did left coset and right coset, you can do these operations of the generators acted from the left or from the right. So that is what I understand. I don't know what exactly you're asking in what context.
some space is left.
No. This is a left action. Left action, which could give you the same set of generators in some permuted fashion. Okay. So it's not space. There's nothing, no space. It's a Lie algebra states. Okay. In what context did I say left invariant? Did I say anything?
No, but there was a question in the Google group asking like why the left and right invariant are same in case of the Lie algebra, but not in case of the discrete group theory. So I mentioned,
left and right ideas and
yeah,
normal.
yeah, maybe they're asking like that.
Yeah, okay. So if you apply it on the algebra, you'll see that whether you do this way or that way will decide its action, whether it modifies, unlike your discrete group, what happens here. Okay.
There was a question on the Google form. There is one question on this Google discussion form that why do we take the character always integers? Like in your lecture, you have shown one example.
Characters in the discrete groups.
Yeah.
Huh.
So you like use the orthogonality theorem and like find the unknown value.
Correct. Correct.
One string find out value 7 by 5 and minus 3 by 5, satisfying the same orthogonality relation. But your values were minus 2, 0, 1. So we are asking that why should we take non-integer integer values?
Okay, so thing is, you may try to cook up some rational numbers, but whenever we are taking a trace of a matrix, which is the matrix representation, we would like those not to be, all kinds of rational numbers. This great orthogonality theorem is beautiful, but we insist on the coefficients of those various irreps like A1, A2, E. You want to find what are the characters, and you will force these are the classes, right? You'll have an identity class, you'll have a class 1, class 2, and so on. You would like to put them only as solutions which are satisfying the great orthogonality, and first step you would like it to be integers. Okay, so don't even try. You can make it complex with modulus being 1, but don't try to put in fractions. It might be possible, but usually all the character tables, when people write, which is like, it's a, you don't even need to work it out. There is the whole catalog of character tables are already available. For us, we are only understanding how the character table has to be written, and they have to be integers. Okay. Is there any way of understanding those integers? I need to think. But usually when we are constructing the character table, we put in that the entries have to be integers or modulus of that entries have to be integer. It could be complex, but the modulus is integer. And then we impose all the great orthogonality theorem and corollary to fix those coefficients, A, B, C, and so on. That's what we have been doing. But if you're asking, can I not work with rational? I think there is no meaning to it, because if you want to compare it, many groups, see, we're doing only very small subset of discrete groups. This could be done for permutation groups up to order, a very large number, and those character tables are already catalogued, and we don't want to violate any of them by putting rational numbers. Yeah, irreducible is something that which cannot be further broken down into, suppose you made the matrix into 2 cross 2 and 3 cross 3. So not just the matrix, the collection of matrices which belongs to the group, you had brought it to this form. If suppose I find another matrix, which kind of breaks it further, completely diagonal, suppose, then you know that that is reducible. But if I cannot find any such G or G inverse, then we say it is irreducible. In the decomposable, there is some definition. Huh?
It means reducible.
No, there is some definition there. I'm not able to recall, but at the moment, yeah, so it is nothing to do with, we know between reducible and irreducible. Sometimes in the matrices, there are matrices which people call it as decomposable and so on. I don't know exactly the formal definition. I have to look into it. You can also check it up.
Yeah.
So there's something called indecomposable.
Does it mean writing in the direct or indirect product of the?
So some matrices of this type with, 0, 1, basically something's on the upper diagonal, others diagonals being 0. We call this to be, I think we call this to be indecomposable. You have to check it. I'm not able to remember now.
Sure.
But it's nothing to do with reducible and irreducible. So you don't need to confuse that with this.
So what does it mean writing a matrix in terms of the direct or indirect product? Is it something different or is it related to this decomposition?
No, I don't think it's not related to that. Okay. There is a class of matrices which is yeah, I don't want to say now. I have to see it, but you can also check it out. There is some subtle difference. I don't want to say that. But what I'm trying to say is a reducible matrix, if you are given, you can further break it. If you can further break it by introducing a similarity transformation, you go how far you can go. Okay, so if you bring it to a 2 by 2 and a 3 by 3 and you cannot find any similarity transformation to further break it, then you say it is a irreducible blocks. That you can say. About this decomposable and indecomposable, there is some subtle difference which I need to see. Yeah.
Joint representation.
I'm sorry, but I didn't understand adjoint representation. Okay. So adjoint representation, see, you know that let's take SU2. Number of generators of SU2 is 3. Okay. You can find the representation which is 3-dimensional. So by this I mean that the number of generators is also equal to the dimensionality of the representation. Okay. So spin J equal to 1. You can write the matrix form for J plus as 3 cross 3 matrix, J minus as 3 cross 3 matrix, and JZ as 3 cross 3 matrix. These are called the adjoint representation. And then you'll ask, what are the states in the weight space corresponding to J equal to 1? That corresponds to J equal to 1, M equal to 1, and then the ladder operator will take it to M equal to 0, another ladder operator will take it to M equal to -1. Okay, so that is the adjoint representation of SU2.
It's kind of
Yes, exactly. In discrete groups, you did regular representation, which is the order of the group. The matrix representation is same as the order of the group, but here the matrix representation, dimensionality matrices are related to the number of generators, because continuous groups, the order of the group will be infinite. You have to look at the number of generators. So if you go to SU3, number of generators, which are these, you can give a Gelman matrix representations, but number of generators is 8. Okay. So you should be able to write a representation which corresponds to 8 by 8 matrix. You should be able to write, which is that collections of those matrices will act on a vector space which should also be 8-dimensional. What I mean by that is these generators, some linear combinations are the ladder operators. So you will get 8 states. Okay. Just like I wrote J equal to 1, M equal to 1, there was one state, then ladder operator gave you the other 2 states. Similarly, you can start with the highest state, okay, And then one ladder operator can give you this, another ladder operator can give you this, ladder operator, ladder operator, ladder operator, ladder operator. And you can also get a ladder operator with this. Okay. So you can get, in fact, there is actually 2 states possible here. You can generate all the 8 states of the octet. An octet is what you call it, is an adjoint representation of SUT. Because the number of states is 8 and the number of generators are. Is that explaining to you? Is this clear to you? Please let me know, then I can.
In one way, we can say that each generator form the basis for this adjoint space.
Agreed. You can do that also. Instead of writing this explicitly as a matrix or a state, you can also say that you have a generator xi and there is a one-to-one correspondent to a state xi. You can do that for the adjoint. We can't do this for other representations. The number of generators will always be 8, but here it is, you are taking an 8-dimensional matrix representation, so it will act on an 8-dimensional vector space. You can play around in the adjoint representation as well. There is a one-to-one onto correspondence between states and the generators for the adjoint. Yeah. In fact, you can show that xj on xi, as a commutator bracket, you can try and match it to commutator bracket of xi. So, all those things you can play around only for the adjoint representation. How to determine number of boosts and rotations in arbitrary dimension? Yeah. So, very simple actually. Okay. So, the thing is, boost is what? It will always include the time and any of the coordinates. So, let me write x1, x2 up to xn. Boost will only try, I can do a boost in the x1t. I can do a boost in the x2t and so on. So it's clearly the number of boosts will be so called a boost as k1, k2. So you can see that k1, k2, how many can be there? Kn. So that will be the number of boosts. Okay. So that will be the number of boosts in the tx. It's basically a rotation which involves one time coordinate and one of the position. Rotations will be mixing any 2 coordinates. Okay. So you have NC2 is, yeah, out of this n coordinates, you have to pick 2 to do a rotation. So this will be the number of rotation. So for if you're doing it for 3 plus 1 dimension, let's say, how many boosts are there in 3 plus 1?
3 boosts.
There are 3 boosts. And 3C2 will give you 3 rotations. Yeah. So you'll have 6 generators.
There should be n minus 1. First time.
No, I have put x1, x2.
Oh.
Yeah. Is that clear? Usually when we do just 3 dimension, we say that rotation about z-axis. Ideally, it is not, you can't specify if you are in n dimension, rotation about an axis. It's only in 3 dimension when you take cross product of 2 vectors, it is also vector. But when you go to 4 dimensions and all, cross product will give you another, 2 indexed objects. So it's better to see the rotation involving x1, x2 mixing, x1, x3 mixing and so on, and that is NC2 rotation. Okay. So you will have so many n boosts and NC2 rotations for an n plus 1 dimensional spacetime. I'll ask you one more question since you are asking me so many. Sometimes, people like to work with 2 time coordinates. Okay, they like to, because many complicated calculations become simpler, and they like to do this. Then you could also have a rotation in the two time axis. That's one possibility. And then you have this kind of boost with one of the time, and similarly you can have, let's say, alpha 1, alpha n with the other time. And then NC2 rotations between the spatial part, and between T1, T2, you have one rotation, okay, in the time thing. And these are possibilities which are also generalizable, and many systems have these kinds of symmetries to look at. I don't discuss it here, but it's possible. They call it as SO2, N in this case. And you can in general write SO some N1, N2, where N1 are the time coordinates and N2 are the space coordinates, with the condition like, if you're doing just SO3, 1, you say dt squared minus dx squared, c squared, dt squared, dz squared is a constant, right? But now you will put in ti squared with I going from 1 to n1. So that's the modification. Yeah.
So he's asking, does it mean conformal group for radius space?
Excellent. So the conformal group, in fact, has this nice property that if you work out the number of generators for SO2, 4, okay, this is what is the conformal group. So if you try to find out what is the number of generators for this, it will turn out to be 15, okay. You can see it, right? If you put 4C2 is 6. And then you have 1 here, which is 7. And then you have 4 plus 4 is 8.
Or 6C2, just
That's another way of doing it. But if you want to do it the way I said here, with 4 plus 4 is 8, 8 plus 6 is 14, 14 plus 1 is 15.
Yeah.
So this is what is the conformal group in 4 dimension. The number of generators are 15. And you have meaning to the conformal generators. You have a scale transformation. You have, the Lorentz transformation, which is your boost and rotations, and so on. So there's a way of looking at it.
it's confirmed the same scale and angle.
It's isomorphic to this. I won't. So this is what they call it as the orthogonal groups in general, but the conformal group can be put in this as an SO2, 4 for 4 dimensions. Sorry, 3 plus 1 dimension space. Yeah. In fact, conformal group SO2, D is true in general for D plus 1 dimension space.
But this is correct. 4C2 is not 6, right? 4C2 is
4C2 is what?
4 factorial times 2 factorial divided by 2
What did you
factorial.
say? This one. So when I can't do 4C2 here.
Yeah.
So if I do 4C2, you will get,
I guess
4 into 3 is 12, 12 divided by 2, which is 6. But 3C2 is 3.
3C2 is 6. It's 3 factorial divided by 2 factorial times 3 minus n into n minus 1 by 2. Oh, yeah, right. Oh, I'm again doing factorial of 5.
Okay? Very straightforward. Any other question? Anybody? I see only iron is active. I don't know how many of them are there, but I'm happy that
There is another way to determine the rank of
goes. Rank is the number of diagonal generators. Okay. Cartan of a matrix. Okay. So you should be able to find
When we read, like we say that, like, we just tell that in SU2 we have one diagonal, in SU3 we have two diagonal, in SU1, like, can we prove there will be n minus 1?
exactly. So the way to prove it is you take an n cross n matrix, and I will put the off diagonal, only the diagonals are there, off diagonals are 0. Okay. And these generators should satisfy trace. Let me call it as G. Trace G has to be 0. That's the requirement. Okay. And this requirement will force that what are the possibilities. So for simplicity, if I take n to be 2 cross 2, n to be 2 cross 2, then what will you write? G to be 1, 0, 0, minus 1. That's the only possible. Anything else is possible? To make it 0, you can put 0 and 0, but that's trivial.
Yes.
Non-trivial matrix is only this. Let's do for n equal to 3. You can have 1, minus 1, 0. That's allowed. Okay. You can also allow 1, 1 and minus 2. What else? What else can I do? 1, 1 and minus 2. You can't put fractions. You put integers. These are the only two possible. Makes it 0, traces 0. One way of saying is that SU3 should sit inside SU2. We'll keep that generator with this being 0. That's allowed. And then this is the only non-trivial one which is possible. And similarly, for n equal to 4, you will allow these two with an additional 0. And then you will have 1, 1, 1 and minus 3. That's the way you treat that to be an identity matrix and then add a non-trivial element. That's the way you fix the number of diagonal generators. So the rank of at least the SUN can be fixed this way. And similarly, SON should also be possible to fix it. Is that clear, Ryan?
There is one more question. Why we don't consider permutation of diagonal elements?
Shuffling of places.
This meant like 1 minus 1 0. Then what about 1 0 minus 1?
Yeah, so you can do various shuffling, but that's just, will not change your physics. Because change of basis by a similarity transformation will shuffle it. But then all your physics are not going to be changed because of your permutations. See, what you call as 0, 1 basis, and 1, 0 basis, I can call this to be the first one and this to be the second one. And I can evaluate expectation value and all. It should not really change. Any other question? How many have registered for exam and all? When is the deadline for registration for exams? You should check that.
I don't check.
Just check and send them a reminder in case they have to register for exam. They should do before the deadline.
Sure.
I don't know, deadline is over or it is still there. Check.
I guess he registered.
Huh?
I guess he registered.
That's fine. Do you know when the deadline was for the exam registration, Ayan? Anyway, if the deadline is still there, you should send them a reminder.
Sure.
Tell them to submit for the. So usually, objective paper, but it may involve you to do some computation before you answer. Sometimes it will be fill up the blanks and so on. Yeah. I think the exam deadline is over, already gone. That's my memory also. So you should check how many people have registered at least.
Yeah, I'm saying it's already gone.
No, the registered people, how many you should check.
Okay, yeah, that's it.
So 2 more weeks are left. Huh? So they are already on the 10th week.
Yes.
And the exams are in May.
I guess it should be.
End of April.
Yeah.
End of April. Any other question you have, Ayan, or anybody else who is online? If you have any specific question, please ask. If there is no further question, then we'll sign out. But you can answer if you have anything, if you want anything to be worked out. We can do it for you. Any other person who has any other questions, please ask us. Then we will try to clarify. And wish you all the best for the exam. I think probably this is the last live session for this semester. 3 are watching, right? So 2 more are there. If they want anything, they should ask us. Okay, there are no further questions. Anyone else has any questions? No further questions, we will sign out. And if you have anything more, you can put it up on the portal. Both Lekha and Pravesh can answer the questions. I will also be able to see things. You can bring it to my notice if there is any other thing. Sure. And regarding this indecomposable, composable, please check it and
Sure.
And then write. Okay. Put in.
Okay.
Okay. And what else? And that's it, I think. Other things I've answered. Left invariant, right invariant is not important. So I will give it to you. So, this indecomposable, I remember some definitions are there. Since I'm only interested in reducible and irreducible, I'm not really given specific thought to this. There is some specific chart. Okay. So we will now sign out. And all the best for your exam. Bye-bye. Thank you. Thank you for